Okay, so we're gonna get forward. It's good to be with you today and for another week here. Um, so we're on our journey to sheaves and this sheep theory through example. And uh, we've reached a watershed moment, important milestone in reaching section 2.3. 2.3 is on presheaves. And as the name would suggest, this subject of presheaves forms a really key supporting set of material and concepts to understand sheaves. In fact, sheaves are presheaves with a further condition for them. Um, but truth is that many practical applications of sheaves, particularly for cellular sheaves on things like graphs, really boil down to take advantage of the properties of presheaves because the properties of sheaves emerge automatically for many of these cases. And it's more subtle than that, but presheaf, the characteristics of presheaves provide us with a large set of the properties that we wish to take advantage of with sheaves. And in many cases, all of those properties. And it's for that reason that I highlight this as reaching an important milestone, reaching section 2.3 in this book. But it's also a reflection of the fact that I really want to, or it's also reflected in the fact that I really want to spend time making sure that there's a really solid understanding of presheaves. Because for sheaves, we're going to build atop that understanding. But we actually are more generally just going to have to really understand presheaves. That provides us, in my mind, a large fraction of what we're going to need to get to is really understanding presheaves. And it's for that reason that I think this week we're going to be spending it on presheaves. We have this section. There's another section on the presheaf action, which I think will be a refreshing perspective for many who have been around presheaves for a while and in their form of C sets, co-presheaves in form of C sets. But even specifically for this lecture, I really want to talk about presheaves and their characteristics. And I recognize that this will be review material for many people here, but it will not be for many joining us ultimately online with these materials and for some of us here. So I really want to make sure we're oriented with respect to presheaves. Now, there's another reason I'm doing this that some of you will recognize, and that is when it comes to presheaves, we have a really rich set of tools available to us in the form of algebraic Julia, CATLab, to represent, manipulate, visualize, transform, find homomorphisms in presheaves. There are bread and butter. There are building blocks at a higher level out of which we build our compositional modeling tools. And I'd like to avail ourselves, if we can, of those tools in this semester, in the project at the least, but quite possibly here in class. So I really want to drill down on this issue of presheaves. And I'm going to avoid getting caught up in the distinction between presheaves and co-presheaves, because after all, presheaf is a category from C op to set. But if we just take another op, we're going to be C op is in fact a category of some sort, call it D. So presheaf is in fact also a map from a category D into set. And I can be concentrating a lot on them, which are called, well, they'd be called D sets, but for a category more commonly C, we'll call them C sets. They're from C, a category C to set. So I'd like to dive into this a little bit. Okay. And again, for many of you, this will be a trip down memory lane. This will be a familiar construct, but for many of you online and here, some, this may be new. Okay. So one thing I want to emphasize is a bit of terminology, and this will really come out in section 2.4, which we will take on likely for Wednesday, and if not for Friday. But for section 2.4, there's an emphasis on the notion of a presheaf action. And the idea here is going to be a concept with an attitude. It's an idea that that is very useful when manipulating these structures. It really can be traced back to group theory and algebraic gadgets there, where we think about the actions of the group. We think about the morphisms in the category of groups, or the group elements as actions acting on elements of a set when we have a representation of it. So we're going to be talking a little bit about morphisms as actions or operations that operate on elements. And I'll speak a little bit about why we think about it that way, either this time or next time. It's actually a very common and prominent idea in certain areas of physics, in mathematical physics, certain areas certainly of mathematics, and in fact in modeling with these tools. So I first want to, this will be a little bit unfamiliar for some looking at this, but I just want to introduce this idea early. For those who have seen C sets before, I'm going to be sometimes talking about the morphisms in a schema category as an action, as an operation, as a sort of button we push to go from an object to itself, but undertaking some action, or one object to another. And we'll be switching back and forth between speaking of them that way and speaking with them as other ways. So I want to talk here about schema categories. Okay, and schema categories are going to play a huge role in discussing presheaves or co-presheaves, because we're going to be dealing with functors from schema categories to set. Okay, that's going to be our focus. That's really at the heart of presheaves, right? So we're going to have a schema category, and it's going to have objects and morphisms. And you may remember last week we talked a little about diagrams and diagrams into set. I don't know if you remember that, but like we have a shape category, and we sometimes map that over into set and like find all functions in set, or find pairs of sets as a map from a pair of objects in the shape category into set. And this is going to have a little bit of that flavor in the sense that the schema category is going to represent a sort of shape, with the properties like we could associate a shape with. So it may have certain commuting conditions, certain relations that hold, and we'll give some examples of that in a minute. But this is a schema category. So we're going to have two objects, and we're going to call them suggestively edges and vertices. Now, don't get caught up that the E dot holds edges. No. It's going to be used in its mapping to represent edges, to mapping it to set. But here is just an object. Here V is an object. And we're going to have a morphism called suggestively source and another called target from E to V. And that is going to mirror the idea each edge is going to have a source vertex and going to have a target vertex. So edges here are taken as directed. We might have multiple edges between two vertices, but for each edge, we'll have a source of it, which whence it comes, from which it emanates, that's the source, and we'll have a target of that edge. Are we okay with that? And each edge will have some identity morphism, and each vertex has identity morphism. Again, don't worry. Just like with the category of monoids where we had the star object, it's not that had secret information associated with it. There's no secret information. These are just objects. Where they will receive their utility is mapping them into set or into fin set, right? And so here's where it gets really interesting. Think of this as kind of a shape that describes what data we're going to maintain and the relationships in it. You could think of it as a schema for a database, hence its name, and we'll come back to that. Okay, a given graph will consist of a map from the schema category into set or fin set. Here we're calling it set. Since we're fin set, we'd have all finite sets as objects. Here we have all sets. Okay, and the idea here, and forgive me, again, some people this will be old hat, but we're going to have V map into the object. Remember what a functor does. What does a functor map? What to what? Tell me two things it maps. Objects to objects and morphisms to morphisms. So object here, V, is going to be mapped into an object in set, and an object in set is what's an object in the category set? Set. And that is going to be the set of vertices of our graph. A, B, C. Edge is going to be mapped, it's an object, objects to objects mapping. The functor is going to map E into the object in set, namely the set 1, 2, 3, 4, 5, 6. Those are going to constitute the edges of our graph, hence E. But a functor is much more interesting because it doesn't just map objects to objects, it maps what? Morphisms to morphisms. So it maps this morphism source to a morphism in set. What's a morphism in set? It's a function. And what is this a function from? Well, it's a function. So the morphism in set, that's an image of source here, goes from the image of the where source comes from, E. So it goes from, this function goes from the set of edges to the set of vertices. Are we okay with that? So that function tells for each and every edge what's its source vertex, hence the name source. So for example, for edge 2, that's an element of this set of edges, right? it maps to its source is A in this graph. So edge 2 comes from A. Okay. By contrast, edge 5, I'll say edge 6 in this graph, its source will be B. And indeed, the source of edge 6 in our graph is B. So this is encoding the rules for a given graph, because this is encoding a given graph, what its source vertex is for every edge. And target here specifies the target vertex for every edge. Say for edge 1, the target vertex is vertex C. Edge 1, the target vertex is C. Edge 3, the target vertex is also C. Right? Edge 6, the target vertex is 6. It goes from B to B. So we could write it out as a little database like this. Again, a metaphor we'll come back to. There are these vertices, A, B, C, and there are these edges, 1, 2, 3, 4, 5, 6. Those are the primary keys of their corresponding tables. There's a table for every object. And then for every morphism coming out of an object, we have a column, a so-called foreign key column, that specifies, what, in this case, vertex. Really, if I had wanted to write it a little bit more fulsomely, I might have named these things different, but this is from A, from B. This is a foreign key column into this table here, and this is a foreign key column into this table. So this encodes a particular graph. It specifies the vertices of the graph, the edges of the graph, and for each edge, what its source vertex is and target vertex is. And that collectively specifies a graph. Any directed multigraph, so in other words, a graph where we have edges, vertices, where the edges are directed from a vertex to another vertex, and where there can be more than one edge between vertices, and we could have edges from a vertex to itself. Any such graph can be encoded as some functor here, because we're providing the necessary information. Are we comfortable with this? Okay. Now, I think it's important to just recognize the need to be careful about something. We're dealing with something over here, and indeed over here, which look themselves a little bit like graphs. Like at first glance, you could be excused for thinking this itself is a graph. But just be aware, like source is referring for a given edge in the graph we are representing, like this edge, what its source vertex is, right? And what its target vertex is in this graph. So source here may look like an edge from the object E to the object V, but it's a morphism, and this is a morphism or a function here that is serving to map this set to this set. Are we okay with that idea? So what does the identity function here do? What does it do for edge to edge? What is it mapping? Every edge to itself. So edge 1 goes to edge 1, edge 2 to edge 2. This is an object in set. It's a set, so it has to have something like this, and this has to have 1 as well. Again, don't get caught up that because there's a loop here, there has to be a loop for every. No. The structure of this graph is not encoded in these particular. It's not like these vertices and the morphisms coming out of it directly encode features here. No, the structure of this graph is encoded in these rules mapping edges to vertices and what edges we have and what vertices we have. Are we okay with this? Okay, let's go have another one. Let's go take a look at another schema category. So this is another schema category. Again, it provides a little bit of almost a shape for us, okay? And here we have just a single object. We're going to call it state. And we're going to have, beyond the obligatory identity morphism on state, we're going to have a functor called next. And I'm going to claim to you, I'm going to submit to you that this category can represent, if we consider mappings of it into a set, different dynamical systems. So let's map it into set. So here's the schema category, and here's set. Or you could be excused for saying, well, I'd like it to be fin set. Fine. We actually do most of our work computationally mapping it to fin set. Okay. So here, each object gets mapped to an object here. So an object here called state gets mapped to a set of states. Just like over here, like V got mapped to a set of vertices, E got mapped to a set of edges. Here, state gets mapped to a set of states of a dynamical system, a set of possible situations in the dynamical system. We call them I, A, B, C, D. Identity just is identity on that set. Nothing too interesting there. Next maps each state in the dynamical system. If you're in that state, what's the next state? So it will map, for example, I to A, meaning if we're in state I in the dynamical system, as described by these possible states, if we're in I, our next state will be A in the dynamical system. If we were in state A at a certain time, our next state will be state B. If we're in state B, our next state will be state C, C to D, and D go back to A here. Okay? Now, again, the fact that this is a circle doesn't have anything directly to do with this being a circle. The structure of this is encoded in this rule of what's the next state for every one of these. This could have been all natural numbers. Well, yes, instead it could have been natural numbers. And we could have just mapped it to the next natural number, right? That would have been fine. It could have been mod 100. We would go from 0 to 99, and then we go back, right? Notice we can also encode it as a database, right? We have a table for each object, again, state. We have a set of primary keys. And then we have a foreign key, in this case, to the same table, specifying what's the next state. That's exactly encoding this rule. It's just a lookup table for this function. Are we okay with this? Okay, so I hope it's starting to dawn on you that, to emphasize my earlier point, the actual schema doesn't have secret information encoding edges or vertices. What gives it that name is that we can, by mapping it over to set, we can represent particular edges where this plays the role of edges, or the set mapped to by E plays the role of edges. The image of E plays the role of vertices here. These play the role of the source of an edge and the target of an edge. Are we okay with this? So functors here are encoding information. We good? Okay. Now, a little bit closer to home for our group, if we wanted to describe causal loop diagrams, putting aside the issue for the moment of attributes and of labels, we could have a schema category like this. We need a V, which through functors is going to, with functors, they're going to use it to represent the set of vertices. We have a set of plus links. and a set of minus links. And each plus link will have a source and target vertex or variable. Maybe we better call this variable in a causal loop diagram. This is more common. And L minus, each of those has a source and target variable. And what I'm arguing is that if we map this over into set, a given functor will encode a particular causal loop, primitive causal loop diagram this way. We will have a specific set of variables, be a set. We'll have a specific set of plus links, a particular set of minus links, and each minus link will have a source for it and a target for it and a source. Each plus link will have a source and target. And the fact that we're saying plus for the link or L minus, that encodes what its polarity is. Are we okay with this? Okay, so here's the challenge proposed. I'd like to encode this causal loop diagram as a primitive causal loop diagram using a schema. Okay, and we're going to have a plus loop up here. We're going to have a minus loop down here. And we're going to put aside for the moment the actual labels on this and focus on the structure. So this could be a plus loop, which is going to have two, each of those loops is going to have two links. Again, these are not morphisms. These are links in our causal loop diagram we wish to represent with a function from this to set. So there's going to be for each of these loops in the diagram we wish to represent using a mapping from the schema to set. There's going to be two links here, plus plus here, minus and plus. So that's what I'd like to represent with a functor. And I'd like to ask, okay, so here we have our schema. And I apologize, maybe what we could do is just to sort of maximize the global happiness function. We'll just put it over here. And there we go. Okay, so here's our schema category. Here we have an object in the schema category called V. Here we will have L plus. I'm going to write it like this. L minus. And then we're going to have source. I'll call it source minus, target minus. So it's going to specify for each minus link in the causal loop diagram what its source variable is, and what its target variable is, and the same thing up here. Okay, I'll do it this way. I could have, through symmetry, I might have done it the other way. But fine. Okay, fine. So this is our schema category. Our shape, as it were. And what I'm telling you is that we can encode that given causal loop diagram, which you saw with this. So what would the set of vertices be? Maybe we will write it out in a table. What's the set of vertices here? How many are there? Well, there are three. Yeah, there are three. Count them. 1, 2, 3. Okay. So I'll call them inf, new inf, and susceptible, or and sus. Or maybe I'll just call infectives like this. I'll say new infectives. Maybe I'll call it lowercase I. Or, well, fine. I'll call it new infectives. And then I didn't do this artfully, but and then number of susceptibles. Are we okay with this? Okay, so that's our V. What's our L plus here? How many plus links do we have? We're going to have L plus here. How many plus links do we have? Let's count them. Hey, get back there. Wait, there it is. Okay, how many plus links do we have? 2 at the top. 3, yeah. Right. Okay. Now the more interesting thing. Oh, now I'm in a pickle. So I need 2 columns here, right? This is just the primary key column. We'll call them 1, 2, 3, for lack of a better one. Say we'll go upper left, left to right, top to bottom. So 1, 2, 3. Okay. Here's L plus. Okay, and then we need 2 extra columns of our encoding of this as a database. What are these? Yes, source plus, target plus. Okay, good. Okay, so link 1, that's this one here. Whence does it come? Where does it come from? From where does it come? New infection. So we'll say N, right? And whither does it go? Where does it go to? I. Good. Okay, link 2. Okay, so we just did, to be clear, hey, get back here. We just did this one. Now we're going to do this one. It comes from what? I goes to N. Okay, I'm going to fill it in here without switching out. Comes from I, goes to N. And this one down here goes from what? S to N. Okay, good. S to N. We good with this? Okay, and then I think you could fill out L minus here. There's only one big, maybe I didn't do so bad. This is L minus down here. And how many total L minuses are there? 1. Okay, and we'll call it, I'll call it A. I could call it a Roman numeral, but that would look like I.
So the key must be different, right?
Well, it doesn't have to be. I mean, I could call it's easier for students to
But you
recognize
can
it.
elaborate, but it is same 1, 2, 3, 4, or
Yeah, it's the same. Yeah. So what should we call this? I could call it fine, I'll call it we'll call it 1. Sure. And it goes from, so what is its source of the L minus? It comes from where? Remember? The L minus, the single negative link. Where does it come from? Hey. Yeah, it comes from, hey, N to S. N to S down there. So it goes from N to S. Are we good with this? Okay. So I would argue that this encodes the structure, encodes variables, and encodes the key linkages between them, relationally encodes the relations. What it's not encoding is the names. To talk about that would take us a little bit aside to attributed C sets and so on. But what it does encode is the relationships, right? It's relational data. It's also sometimes called combinatorial data because it's built up little bit by little bit. We're composing this this broader structure of a causal loop diagram out of sort of various pieces. And we're going to see that terminology later for simplices, which are combinatorial structures to represent graphs or higher dimensional structures. Okay. Okay, so here we have an encoding with the schema of a particular causal loop diagram, right? Where we have like, I should have drawn this earlier. This is I, this is N, this is S, right? And we have plus, plus, and we have minus and plus here like that, right? Number of new infections. So as new infections go up, susceptibles tend to go down compared to the value that they otherwise would have had, all other things being equal. As susceptibles go up, number of new infections per week, say, or per unit time tend to go up. As in fact, total number of infections go up, new infections go up. As new infections go up, it tends to drive larger the number of people who have infection. Are we okay with this? This is a plus. This is a minus, and we've encoded it with this diagram. Okay. So schemas, it's not that schemas encode information. Schemas together with a functor represent structures. Are we good with this? Okay. Now, I want to highlight that we could undertake this for a wide variety of structures. We saw earlier how we could have monoids, for example. And monoids have a single object, right? That's identity, or excuse me, and then identity here, identity on this, and then we could have we could encode monoids as a category this way, with this might represent 0, this represents 1, or something like that. If we wanted mod 2, that's all we need. This we don't even need this other one, but maybe we have 2, and then we can go back to 0, right? That's encoding a monoid as a category. But I want to note that we've seen another way we can encode a monoid. I mean, this gives us actually another option for encoding monoids using this structure. And in fact, it's very common in mathematics to use structures like this to encode larger structures. In other words, to use schema categories with a mapping into set. So for a monoid, we could have simply we could have like a multiplication operator. Ooh, that's not what I meant. This is okay. I've already overloaded that plus, right? And we could map it over into set. What would this object be mapped into? It would be mapped into the elements of the monoid, the possible values it could take on, say 0 and 1. What would this be mapped? Be mapped to identity is right. It used to function as 0, but now it's actually mapped to identity. It has to be, right? So if we have set, this could be the set of elements of monoid, say 0, 1. We map this over into this, right? And then what we can end up doing here is end up taking with the monoid, we can ask, what is, I called this plus. I'm actually, that was a mistake on my part. I'm going to say next for the monoid. Like we're going to add to some element with the monoid. So it's going to take a monoid, a given monoid element, and add it. So it's gonna map from this set to this set again and again and again and again, evolving this set. This is actually not a good example. I'm sorry. What I really wanted to show you here, though, was the actions of a broader set of structures, which is going to be what's called a group. And here, what we would be having is some structure where we might have a group action, G, and then we'll have a negative of that action, G minus. And that would apply to this set some group operation on this set. So we're applying some action to this in accordance with the rules of the group. And this would map back. So this would invert a given group action. So we might have over here actually and some underlying vector space, and we will be performing group actions on that vector space, sort of rotating things, for example, in the vector space. So we might, with a group action, rotate it by 90 degrees, for example, something like that. So the group action here would be sort of applying some operation here, taking a vector as encoded as a set and rotating it by 90 degrees in this basis set associated with the group, and then, or associated with this representation, and then applying it 90 degrees again, maybe 90 degrees again, and then it would turn it back to this. So here, the group action would be this morphism that would update the state in accordance to how the group acts. So it would rotate, or it would flip in one axis or flip in another axis. But for each action, there's a minus version of the action, inversion. So here, rotate right by 90 degrees. What's the inverse of that? Yeah, go back by 90 degrees.
Is translation also like translation and reflection also a group action?
Yes.
So you can just
precisely. It's a beautiful group action. That's right.
Conformal group, right?
Yeah. Yes. Well, so there's a variety of groups associated with this. There's SO3, which is this sort of beautiful orthogonal group, which involves, I think, small actions. But there's a variety of these groups that involve rotations and flips. And the idea is that, like, if you go here, so tell me, if this is rotating by 90 degrees for a case here, what would G to the fourth need to be equal to then? So 1, 2, 3, 4. What does it equal? Yeah, G0 or identity, actually. So ID on this, the ID morphism. And G, and then inverse of G would be identity. Here, do you understand that? But if we had multiple types of things like flips and rotation, you would have multiple actions here. You'd have group actions, and it would act on an element, a vector, say, to rotate it or flip it or what have you, in accordance with these group actions. So it turns out this is a very powerful notion in mathematics. We could take abstract objects and then we can represent them in a particular domain, like a particular vector space or a particular context of set behaviors, where you interpret it in a certain domain by having a functor from it into your appropriate domain. So this is kind of some sort of abstract notion, but you interpret it in a certain way here in this particular domain. And the interpretation might be different, a little bit different in R2 versus R3, but you might have other structures that interprets it in other domains, maybe with a discretization or something. Anyway, so these are called group actions here, these ones, because they act on things like rotating a vector, right? Or flipping something. And this notion of a group action is going to carry over. Like you'll hear that term, even in like Cat Colab, you'll hear them using that term. And in the book, there's a discussion in the next section on group act or on actions. And these go by the name of right actions for most of our cases. And we can view these things as actions. And the author talks about viewing them as button pushes. If we have a plus link, we push a button and we get its variable. We have a variable or we have a minus link, we can push a button and get its source. This is like pushing a button to rotate our vector or what have you. Okay. So that was a little bit on the terminology and philosophy that we'll be operating with in the context of this book and when we're in this area. I do want to pop up for a moment and just note, if we encode causal loop diagrams, it bears noting that they can be placed in a category, right? We can have a category of causal loop diagrams, and where the morphisms are structure preserving mappings between them. For example, they may map multiple vertices onto one vertex. So a given map here from one causal loop diagram to another might map, several vertices here into one, or maybe it embeds one inside another diagram. It places it into this diagram, right? This is our category of causal loop diagrams. And there's always an identity morphism. What would the identity morphism do on a diagram to itself? What would the identity do? Yeah, it would just leave it as itself, right? Leaves it unchanged identity. Now, I hope those encountering this for the first time will also recognize the generality here of these ideas. So for example, we could have a schema category that has person object, home object, dog object. It maps person object into a set of people, maps dog objects into a set of dogs, home objects to a set of homes, and perhaps for each person, where it only so, there's a home. So the functor is going to interpret person home as a set, as a function mapping from the set of persons to the set of homes. It's going to interpret caregiver as a function. The functor is going to map it to a function from the set of dogs to the set of persons. And it's going to map dog home to a function from the set of dogs to the set of homes. Are we okay with this? Okay. Now, what I want to emphasize with this slide, though, is that as a category, there might be, we specify category by specifying objects, morphisms. We provide data for category by specifying the objects, the morphisms, the rules for composition, And with those rules for composition are the relations, right, between things. So for example, here, what is the fact that this is a commuting triangle saying? What is this saying? It's saying something actually very sensible.
Dog has a home, dog has a caregiver, and caregiver's home same as dog.
Same as the caregiver's home is the same as the dog's home. So if a dog is a caregiver, somebody that takes care of it, they live at the same home. And that's what this would be saying. And so if we map this over into set, to be very clear, because this is enforced by composition, what this is saying is this morphism and this morphism in the schema category is the same as this. And because functors honor composition, if we map this into set, its representation as a in set, just like we did earlier, its representation in set would honor this. So we'd have a set of dogs, set of persons, set of homes, and for each dog, if we consider the caregiver for that dog in that as a mapping between sets, a set of dogs, a set of persons, and we consider for each person what their home is, it would match up with the home for the dog. So in other words, the encoding of this as a category, like we did up there on the board, would honor this. Would honor this relationship from the schema. Now, this is an extremely powerful notion. It's not just that, our encodings here are just sort of arbitrary bits of data. It's the bits of data that carry the structure of the source category. They honor that structure. They honor the composition rules of that structure. And when we represented a group in that way, we also needed that to be the case, right? If you applied a group action and then it's inverse, you get identity, for example. And so it is here, but it serves very practical needs. We actually have a way of describing, of enacting these schemas as a mathematically rigorous object that retains the structure of this category because we have a functor mapping this into set. So to sort of ride this notion a little bit further, we've seen the schema earlier for graphs. The schema for graphs look like this, right? Two object morphism from E to V, two morphisms from E to V, and two identity functors. The schema for symmetric graphs looks like this. In many ways, it looks the same. We have these identities with E and V and so on. But there's an important difference. And one immediately obvious component of the difference is we have this so-called involution operation here. It's a morphism from E to E. Okay. And it's not merely that, though. It has certain relations that are assured. So the involution, notice where the involution comes, whence it comes and whither it goes. It comes from E to E. So for any edge E, we could take its involution and we'll get another what? So again, we'll be mapping this over to set. So for any edge, and that as represented in that set, we can get another what? Edge, which is its reverse edge. But notice it doesn't just stop there. It's not any edge. It's not given an edge, we get back some random edge. No. We get back an edge whose source is the target of the original edge. So if we had an original edge in our graph and we take its involution, we consider what's its opposite edge. Well, the source of that opposite edge is such that it's the target of the original edge. That original edge, we take its involution and we consider a target. The target of that is the source of the original edge. So let's play with this idea a little bit, if we could, because this may seem a bit abstract, but we'll see how it can play out here. I'm not sure where to put it. Oh no, that's not what I want to do. Okay. Maybe I can. You don't. Whoa. Okay. Okay. This is thanks. Sorry, I don't need that. Oh, I got screen real estate. Let's see if I can make this all the physics work. Okay. Okay. Okay, here we go. So we have this E, this is our schema. EV, this is source, this is target. We have these identities. I'm not going to draw the identities. And we have involution, which an edge tells us the sort of what its reverse is. And we want to represent a graph like this, say, where we have one particular, we have two vertices, and we want to have a vertex from X to Y and Y to X. This is what's called a symmetric graph. And I could elaborate it, but it's gonna have, yeah, okay, fine. Let's have a Z, and for every edge, we're guaranteed by the fact that it's symmetric to have a inverse edge. So you could think of this as kind of representing something kind of similar to the properties of an undirected graph, because for every edge we have a reverse one, right? If so-and-so if X shares needles with Y, Y shares needles with X. Okay, so how would we encode this? What would the set of vertices be? That's kind of easier. What are the set of vertices? We don't have any morphisms out of it. So what are its, how many do we have? X, Y, Z. Okay, now. How many edges are there going to be? 6. Something like that, right? And hope you'll forgive me for just labeling them. Yeah. And maybe we'll label them this way. Yes. Lexicographically. Okay. Okay. Now, what are the columns here? So, yeah. So this is a table for E, and we have a column for each morphism out of it that's going to give the rule for the function that this turns into, right? When we map it over here. We're encoding in a lookup table, the functions. Okay, so this is going to be source. Maybe we'll call it involution, again, lexicographic, source, target. Are we okay with that? Okay, so for let's do the obvious ones first. We know well, no, let's go to the heart of it. I think you could fill in source and target pretty straightforwardly. Well, sure. Let's go through each of those. Okay. So the source of edge one is what? What is the source of edge one? X. What's the target of edge one? Y. What's the source of two? Edge two. Target X. Oh, should I be? Yes. Okay. Good. Okay. Edge three. What's its source? X. Okay. And then Z. Okay. And how about someone else's voice too?
Our source is Z.
Yeah.
Target is X.
X. Yeah. 5.
Source is Y. Target Z.
Okay.
And
6.
Z Y.
Good one. Good. Okay. So this is kind of old hat. You wasn't old hat when you came in here, but now it's kind of old. Okay. Great. Okay. Now the question is going to be involution. Involution is going to specify for a given edge what edge is its reverse. So what's the reverse edge for 1?
2.
2. Because it's, and notice the properties here. Notice the properties that we're trying. Well, maybe let's fill in the, okay, 2. And what's 2's reverse? 1. Okay. So let's notice these properties that we want to ensure. Okay. So first of all, if we square involution, the involution from an edge, if we have edge E and we apply involution twice, we go from 1 to 2, and then we apply it twice, it brings us back to 1, right? Okay. Let's ask, okay, if we take an edge and we apply involution to it, so we get, say we take edge 1, we apply involution to it, we get edge 2, and then we take the source of edge 2, X. I'm saying that that has to be the same as the target. Excuse me. We take an edge 1, take its involution 2, we take the source of 2 of that one, is Y. I'm saying that has to be the target of our original Y. And similarly, this last one, if we take a given edge, say 1, and we take its involution 2, and we consider for that the target of it, that's X, that has to be the source of the original. Are we okay with that? Okay. So now you can tell me probably pretty quickly based on this, for edge 3, what's its involution?
4.
4. And for 4, 3. For 5, 6. And 6, 5. And the point is, by mapping this into set, we have captured a specific instance of a graph that honors these properties. And I haven't written down these properties, these relations, right? Which are key here, absolutely key. Every bit as key as you know, this structure here. But we have not just any encoding as data, not just some random data. We have data that honors the mathematical structure, that is, in some sense, rigorously encodes the underlying mathematics by virtue of mapping this in. And that property of having this data that rigorously captures the underlying mathematics is what's going to let us realize the magic of sheaves. It's going to let us realize these properties that we're going to be having with sheaves. A very large fraction of which we're going to just inherit from presheaves. Okay. with these so-called restriction maps and their commuting conditions. So what you've seen here in the small is a reflection of the power of this approach of encoding things with functors into set, and these so-called presheaves, that's going to take us most of the way to where we need to go for sheaves. And if you understand this idea of the mapping honoring the composition and the properties of that schema category, you will be a long way towards understanding why sheaves have the properties and the advantages that they do. Okay, so these notions are not of small importance. They're not at all small matters or distractions. They are at the heart of the enterprise that's underway this semester to bring us into contact with sheaves. Okay, so I'm